Hello everyone, my name is Resul Saritas. I am a PhD student in Systems and Engineering at University of Waterloo. Today I am going to talk about dynamic scanning probe lithography. Scanning probe lithography method is alternative way of fabrication of micro and nano devices with minimum use of equipment in clean room. Clean room fabrication methods including FIB and electron-beam lithography methods are limited to small area patterning, long operation time, requirement for high vacuum, and inability to directly pattern a wide range of the materials. Those limitations have motivated the exploration of unconventional lithographic methods. As you can see on the figure on the right side, there are various scanning probe lithography methods, such as thermal, diffusive, electrical, and mechanical. The challenges of these methods are their slow fabrication process in the order of the 0.1 to 50 micrometer per second, and they require closed-loop complex control systems. Although scanning probe lithography methods reduced complexity and cost in the fabrication in comparison with EBL and FIB, high throughput and low cost patterning of the large areas has still remained as a challenge. In this report, we introduce a new surface patterning method called dynamic scanning probe lithography. It has its own unique features, such as angstrom to microscale thickness resolution, centimeter size patterning, applicability to a wide range of the materials, and high throughput. You can see in this image that a sharp scriber that has been mounted on a 3D nano stage through a spring and damper suspension mechanism. And suspension mechanism enables the scriber to move up and down, and thereby creating an adaptive working distance, a flexible working area, and without a need for complicated feedback systems. The suspension mechanism compensates the variation in surface contact force and thereby producing long and uniform surface patterns. We are also using our dynamic scanning probe lithography method for fabrication of the microchannels and nanochannels. You can see that in this slide, the microchannels, they are fabricated on the PMMA substrate, and those channels are 1 cm long, 2.5 micrometer wide, and they are also 700 nanometer deep. We used our d-SPL method for fabrication of backgated graphene field effect transistors. We recorded a video demonstrating fabrication of the source and drain electrodes as well as their pads. As can be seen in the video, the scriber tip removes the nano thin silver layer deposited on the silicon dioxide. You can also see an optical profiler image of the fabricated electrodes in the figure top right. Then a microplatter was employed to place graphene between the source and drain electrodes to create the channel. Optical image of the fabricated graphene transistor is shown in the figure bottom left, and it is IV characteristics shown in the figure bottom right. The results show that the d-SPL can be also successfully implemented for fabrication of graphene field effect transistors. Thank you so much for listening.